Right, this is our scenario for today. The data above shows the height in inches and weight in pounds for 14 football players. So we have their height in inches and their weight in pounds. We're going to construct a scatter plot on our calculator with the height being the explanatory variable, that's going to be the x, and the weight being the response variable, that's going to be the y. We're going to get a least squares regression line, and then we'll graph it to verify that it fits, and then report what they're asking us to report. So in the interest of time for this video, I already have the height put in L1 and the weight put in L2. And I'm going to mark this up top to keep track of what's where, because we're going to have a couple other lists happening soon with this activity. And I already set up a stat plot. I already built a window that makes sense in the context of the problem. Data certainly appears to be reasonably linear, and it turns out that it is. We're not really going to investigate that any further with today's activity. All right, quit out of there. Stat calc. We are going to get a least squares regression line using the preferred AP format. And we'll store this directly in Y1 and calculate. All right, so our least squares regression line here is y hat equal to -701 point, and I think with these I want to go 3 decimal places, 908 plus, I don't have quite enough room here, 855 x. Our r is 0.947. Excuse me, and the r squared, about 0.898. Now, just as a reminder, if this were an actual free response question on the AP exam or quizzes or tests we take in here, we'd want to explicitly define x and y. Not really the goal of what we're trying to accomplish for today, but just as a reminder of that's something that should be taken care of in a more formal situation. All right. Number 2 says convert the heights to centimeters and the weights to kilograms. So what I'm going to do is I'm going to make L3 height, and we're going to put that in centimeters. And I'm going to make L4 be weight, and that's going to be in kilograms. And the conversion factor that we're going to use here for this, hang on one second, take a peek at my notes, which slipped away from where I just was. We're going to take all the heights, or we're going to take all of L1 and multiply it by 2.54. And for the conversion factor with the weights, we're going to take everything that's in L2 and we're going to multiply that by 0.45. So I'm going to go back to stat edit. I'm going to put the cursor on the title of L3. And what I want to do is take everything in L1, so that's second L1, and times it by 2.54. And hit enter, and L3 is going to populate with all of the heights now measured in centimeters. Okay, I'm going to put the cursor on the title of L4. I'm going to take everything in L2, second L2, and multiply that by 0.45 and enter. So L4 populates with all those weights in kilograms. So what they're asking us to do is to calculate a new least squares regression line for the converted data. So what we're going to do here is we're going to do L3, L4 when we run our line of best fit. The first one was using L1, L2. quit out of there. Stat, calc, choice number 8. I'm doing L3, comma L4, and we will store that regression line. We may or may not need it, but just so it's stored somewhere in Y2. And I am going to calculate that and record that information. And it'll space out a little bit better here than it did in the last one. Y hat is equal to negative 315.858 plus 2.277 x. R value 0.947, R squared 0.898. Okay, referring back to the original data, calculate the least squares regression line with weight being the explanatory variable and height being the response variable. So we're back to the original data, L1, L2, except now we're going to switch the x and the y. Instead of the x being the height and the y being the weight, they're going to reverse. So when we run the regression, it's going to be L2, comma L1. Stat, calc, and choice number 8. And now we are doing L2, L1. And not sure if we need to use this for future reference or anything, but we will put that in Y3. Calculate. And that gives us Y hat is equal to 56.641 plus 0.0698, so that'd be 0.070. X, and we get 0.947 and 0.898. All right, question number 4 from this handout says, what do you notice? Does this make sense? So one of the things that should have grabbed your attention, R is the same, R squared is the same. Well, if the R's are the same, the R squared has to be the same. That's not necessarily overly profound. The thing we want to address here is that R being the same. All right, does that make sense? And then how do we connect it to some other things that we've talked about? Well, looking at here to here, changing units, okay? Changing units is not going to affect the R value. Now, looking at where R comes from, and this is our formula sheet that we will be given for when we take the exam. These are the things that are relevant to lines of best fit. So R comes from this formula right here. Basically what we're looking at here are z-scores. Well, we remember from z-scores that changing units in z-scores didn't affect the z-score. So if we're talking about changing units here, that connection with it didn't matter with z-scores in terms of z-scores changing, kind of follows that that makes sense. So regardless of what units we measure our data in, whether it's in inches or centimeters, whether it's in pounds or kilograms, or we can mix and match height in centimeter with weight in kilograms, etc., that R value is always going to be the same. All right, next thing we got going on is from here to here, the X and the Y traded places. What we did is we switched what was the explanatory and what was the what was the response variable? Well, looking back at the same formula here, if we switch this and this, algebraically, numerically, it doesn't change our answer. So another property of correlation is the fact, in addition to not mattering what units we measure our data in, it doesn't matter which one is the explanatory, which one is the response. The R remains the same. All right, I'm not going to write that out here in the interest of time. Also today, there's a summary sheet of facts that we've talked about when it comes to correlation. That stuff is listed on there. Right, next thing on this handout, it says, could we obtain the least squares regression line from 3 by manipulating the least squares regression line for number 1? Why or why not? What implications does this have? All right, so what this is getting at here is if we just switched x and y here, could we have simply switched x and y here with these two equations? Well, let's see how that plays out. So we have y hat is equal to negative 701.908, little dyslexia there, 908, plus 12.855x. So if we switch the x and the y, and then resolve this for y, what do we end up getting? So that's over there. So the x plus 701.908 equal to 12.855 y hat. I'll switch sides of equals and I'll divide through by the 12.855 number. Calculate that guy right there with the decimal approximation. And that's about 0.0078. No, I'm sorry. 0.07. I'm going 3 decimal places, right? 8x. And this one here, 701.908 divided by 128.128. I'm sorry, I'm having issues here. 0.855. Take 3. And that turns out to be about 54.602. All right, let's take a look and compare to down here. So we have, I guess I went algebra here, flip the order. That's more appropriate. So we have 56.641 versus 54.602, 070 versus 078. All right, now there are a couple things going on here to be considered. One of them possibly is we have a decimal round-off error. We went 3 decimal places here. Maybe if we kept more decimal places, they would have turned out to be exact. Or maybe there truly is a difference in the numbers. They would be really the only 2 plausible things to examine here. It turns out that this is not due to not having enough decimal places, that there truly is a difference between this equation and this equation. And the place to go to illustrate that, back to our reference sheet here. This, or this, I guess it could be either one, indicates that A is the y-intercept and B is the slope. B comes from R sy divided by sx. All right, the only way that this can be the same as this is if the r value is 1. If the r value is not 1, then you're not going to get this line from this line here, or that equation from that equation, or vice versa. The implication of this is when you're using these models for the purposes of describing data and making predictions, this original one we got is only valid for given an x, find a y. If you want to reverse the order of prediction, given a y, find an x, what you have to do is rerun your line of best fit and get this guy. You can't simply algebraically manipulate the first one. Now the answers are pretty close, and in most algebra-based classes, including my pre-calculus class, when we get some kind of equation or line of best fit, we use it for making predictions in both directions. That in certain situations, such as an algebra class, a pre-calculus class, the numbers are close enough where we're emotionally comfortable going in both directions with those predictions. In the true statistical sense, you shouldn't be doing that. So this here is valid for given an x, predict a y. This is not valid for given a y, predict an x. You should rerun it, switching this, and then be using this equation for that order of predictions. So that is the implication. For all the problems that we've done in this class, we've never done a predict an x given a y from a line of best fit because it's not appropriate. If you were happen to be asked that, then what you'd have to do is rerun your line of best fit equation with the variable switched. All right. So the goal of today's lesson, or the goals I should say, one of them being pure calculator skills of knowing how to use lists to do things like converting units, making the observation of some important correlation facts that we need to know, which are correlation does not change by changing of units, correlation does not change by switching x and y, but these equations are only valid in particular directions, which we just specified. All right, next thing we're going to talk about for today is an overview of things we've already talked about with correlation and the new things that we've just illustrated here. So this is the formula in order to find correlation. Again, it is one of the 4 formulas you get on your AP reference sheet that have to do with lines of best fit. Okay, by your book's definition, the correlation R measures the strength and direction of the linear association between 2 quantitative variables x and y. Although you can count a correlation for any scatter plot, R measures the strength for only straight line relationships. Correlation does not describe curve relationships between variables, no matter how strong the relationship is. So you can always get an R value. The calculator will spit it out, but it may not always be valid. If your original scatter plot clearly is a curved pattern and a line is not appropriate, then an R value is meaningless. Or sometimes there is a curved pattern that's not necessarily obvious within the original scatter plot, but your residual plot shows the curved pattern. If you got that curved pattern in residual plot, again, R becomes meaningless. The correlation indicates the direction of a linear relationship by its sign. R is greater than 0 for a positive association, less than 0 for a negative association. So positive association means your data is rising to the right, negative means it's falling to the right. A positive association means that higher values of x correspond with higher values of y. Negative association, higher values of x correspond to lower values of y. Correlation always satisfies R is between -1 and +1 inclusive, and indicates the strength of the linear relationship by how close it is to -1 or 1. Perfect correlation, plus or minus 1, occurs only when the points on the scatter plot lie exactly on a straight line. Okay, that's extremely unlikely to occur in real-world data, prepackaged algebra-based problems that can occur. Okay, a correlation of 0 doesn't guarantee there's no relationship between two variables, just as there's no linear relationship. A value of R close to 1 or -1 does not guarantee a linear relationship between two variables. A scatter plot with a clear curve pattern form can have a correlation that's close to 1 or -1. Always plot your data. Okay, so you can create data sets that are clearly linear, clearly curved, but when you fit them with a line, they still produce an R value pretty close to 1 or -1. So you can't look at just the number by itself. You have to look at the number in combination with the original scatter plot and sometimes also the residual plot. Okay, the correlation R itself has no unit of measurement. It's just a number. That's an important thing on free response questions. It's an easy place to lose points by putting some kind of label next to R. If your R has a label, you're not going to be getting full credit. It's just a number. All right, connecting back to lots of different things, correlation does not imply causation. For example, looking at data from the last 10 years, there is a strong positive relationship between the number of high school students who own a cell phone and the number of students who pass the AP statistics exam. Does this mean that buying a cell phone will help you pass the AP exam? Not likely. Instead, the correlation is positive because both of these variables are increasing over time. Okay, correlation ignores the distinction between explanatory and response variables, meaning switching the x and y does not affect the correlation. And we just looked at that with this example right here. Okay, it does affect the overall equation. This equation cannot be obtained directly from that or that from this, but the R value itself does remain the same. Correlation is not resistant, so outliers can greatly change the value of R. And we've addressed that, I believe, in a prior lesson talking about the influential data points. And correlation requires that both variables be quantitative, so it makes sense to do arithmetic indicated by the formula for R. We cannot calculate a correlation between incomes of a group of people and what city they live in because the city is a categorical variable. In everyday language, it would be acceptable to talk about a correlation between where you live and how much money you make. But in terms of the strictest statistical sense, using it as a statistical vocabulary term, correlation has to be involved with quantitative data. There can be an association between where you live and your income, but you're not allowed to use the word correlation. All right, and I believe that is a wrap for today's lesson.